So it's a pleasure to be here. I'm going to have to explain that intro, it sounds like. I will, because there's a lot of science in there, but I'll be able to do that. I'd like to really thank West Florida for inviting me and IHMC for hosting me, and then the Smart family. And it's always, there's two hard things in life. If you're the professor of energy, that means you have a chair. And if you're not very energetic, if you have a professor of energy, they take it away from you. And if you come and give a smart lecture, if you're not smart, I'm going to hear about it. So I'm going to try to live up to the family name tonight. And it's a joy to have Mrs. Smart here. So today what I want to do is talk about energy and in a different way. And you can see right here, it starts off, personalized energy for one person. This figure, I didn't even know this. I have a big research group, 40 graduate students and postdocs. And you really, I don't even know most of their names when it's 40. That's a joke. Somebody just went like this. They thought I didn't. But they all have talents, and they're always hidden talents. And this one fellow in my group who was the most inauspicious of anybody in my group, I found out is really famous in Japan because he created this character and he has this massive cult following. And if they meet Tim, they'll be very disappointed when they meet him. But this, I had him, because there are kids with purple hair that are all studded that visit my lab to meet the great Tim Cook. And I had Tim last year draw this because it gives you a sort of feeling about what I'm going to speak about today. And that is a single person. They're holding the sun in their hand, so it's going to be solar energy. It's actually an artificial photosynthesis, and I'll explain that dice cube to you later. And then that's the grid. That's how you live, and you can see I'm out to destroy it. All right, so that's what we're going to talk about today. I always made fun of the grid, and I know I can't destroy it, but engineers at MIT are really tough. And they've started yelling at me and saying I'm absolutely a lunatic for thinking I can destroy the grid, which all that says to me is they're actually starting to believe I'm getting close, or they would ignore me. So we'll see how close I'm going to get. So I want to get the energy right for one, and then this is the important point, times 6 billion, and I'm going to explain that. But it turns out everything in your society, that when you need a lot of it, you manufacture it, right? So if you need a lot of things, you make it, except for one thing, energy. In energy, you only make one big thing, and then you distribute it. So it's actually the anomaly in terms of how we live. And so all I'm doing, and what I want to do tonight, is talk to you about just returning to the old days of just good old US manufacturing. That's number one. And then go back really to the old days and then use the sun as your energy source, because you should realize we've only started using a different energy. So for 2 billion years, the Earth has been powered by the sun. And only in the last 200 years did we decide to take a different route, and we're screwing everything up. So I want to just go back for what we did well for 2 to 3 billion years. It's that simple. Okay. So let's talk about this issue about solar energy for the 21st century. And where's the mic? Here, I got to be over here maybe? Oh, good. So this came from a journal called Science. It's a very prestigious journal. And Chimichan wrote, if our black and nervous civilization based on coal and oil should be followed by one with solar energy, that wouldn't be harmful to human happiness. And then what he said is it's to fix solar energy through reactions that master the photochemical processes that have been the guarded secret of plants. So here's a person that's in Science magazine saying we should probably use the sun, and we should do it with photosynthesis. And that is very appropriate for the 21st century. The problem is, I kept the date out here. He wrote that in 1912, okay? And so if somebody writes something like that over 100 years ago, and you thought that they wrote it last week, it must mean the most important thing is we're not really serious about this. right? Because nothing should be 100 years old and still ring true. So the first thing I'm going to sort of prove to you is we don't really care about energy, even though we say we do. I will say, and by the way, I'm going to start off, and it's going to sound very depressing, and by the time I'm done at the first part of this talk, you're going to figure, just go home and just wait until the world to end, okay? But actually, there's going to be a big message of hope. And the first message of hope is I've never seen more change in my lifetime in the last 10 years with regard to energy than anything else I know in society. I mean, it's on everybody's mind, no matter who you are, but all for different reasons. That's the only reason why it has legs, okay? But the bottom line is, I think we've turned the corner, at least as a society, and we're realizing we need to deal with this. So what I want to do first is tell you how you're living now, because a lot of people don't know that. And a few years ago, I did these global energy calculations. I'm going to explain. Every calculation I do, I can do in real time. So I'm going to show you how I do these in real time. So the first thing is I need to define a unit, and that's 12.8 terawatts. So that's not energy, that's power. It's a 100-watt light bulb. So when you have that light bulb that's shining on me right now, that's got to get energy to be powered. And so the power that you get out of that, you have to feed it. And this is a 100-watt light bulb. You're burning in 2000 a 12.8 trillion-watt light bulb. That's what the amount of energy is we're using. And power is energy per unit time. So you don't need to worry about whether I'm speaking about today or am I talking about energy for a week. It's energy per unit time. And so we're burning a 12.8 trillion watt light bulb. And then over here in these numbers in parentheses, I'm showing you that almost all that energy that powers that light bulb comes from oil, gas, and coal. So I haven't told you anything new. In the year 2050, I can calculate how much energy you're going to need. And I'm going to calculate that it's 28 terawatts. So we're at 13 in 2000, and in 50 years from now, from 2000, so now only 40, we're going to need 28 terawatts. And that's an easy calculation, right? And it works. I can go into the future, and to test myself, I can go backwards and calculate in 1930 how much you used. And this formula works. And you just have to know three numbers. One is how many people are on the face of the planet, population. So if I know how many people there are. The next thing is GDP, gross domestic product per person. So in each country, I can take the United States and say, on average, we make this much money as a country and divide it by the number of people. So that's wealth, right? And then the last thing is energy intensity, and that means the amount of energy you use to drive a GDP. And so if I can use the same amount of energy and make my GDP go up, that's good. And that's called conservation. So all I did is I put a formula on conservation, which is energy use per GDP. Right? So if I know energy intensity, which is energy used per GDP per dollar, if I know how many people there are and I know how wealthy the population is, I can calculate energy for anybody. That's it. It's that simple. And so when you do that, you can get 28 terawatts. Now you have to figure out, what did I put in here for numbers? So the first thing is for population. Right now you're at 6.2 billion. You will be in 2050 9.4 billion. By the time I'm done speaking in the next hour, 240,000 new people will be born into the world, net. Okay, so this is going to give you a feeling of why we need so much energy. I used the GDP that was very conservative. I used the global average, and the reason why that's conservative is because it's 2.3% per capita growth, but it turns out that, for instance, China is growing at 6.6% this year. They've been up at around 10 and 12%. And even in this economic downturn, I was with the premier of China in Davos last year, and he promised they would grow at 6%. And he's even over his promise. Okay? So 2.3% is low. but I'm going to give it to you, and that's why I have this higher number there. And then finally, what did I do for energy intensity? Because a lot of people now use these numbers, and then when I'm done, when people are done speaking, if I go to a talk and see somebody using these numbers, then I'll see all the questions saying, we need to conserve more. But they always forget, in my energy intensity calculation to get to 28, I assume that we're going to conserve 100% of the energy we use today. So I made the assumption you're using 13 terawatts, that you will save 13 terawatts of energy in the year 2050, which is unprecedented. All right? So what that says is you're not going to conserve your way out of this problem. So in most of it's due to this population drive, and then poor countries wanting to become rich, which we all want, because for whatever, and you could, for a number of reasons. But one of the biggest ones, my colleague is the ex-CIA director, is everybody knows you get a much safer world when people can all prosper in it. So that's why you should all want people to be prosperous. They aren't as angry. So here's the problem, and you're going to need 28 terawatts. So at the end of talk sometimes I'm going to preempt, like, what can we do now to solve this problem? What's the biggest thing we could do? Well, now you know the equation, so what's the biggest thing you want to do? Die? Somebody said die? I'll make sure that's going to happen, don't worry. Birth control. Yeah, you want to control population. So if I could keep the population from going to 9.4 billion, we'll need a lot less energy in the future. Right? So if you go on the webs, you'll see there are terrible things people blog about me because I'm saying I should have social engineering to control population. So now here is my great social engineering Darth Vader plan to control population. Educate poor females. So every study has always shown if you educate poor people, and especially females, birth rates drop like a rock. Right? So I'm trying to convince you we don't care about energy that much, because if we did, the first thing is you would all be stamping your feet to educate poor females. That's the biggest thing you can do right now. Right? I'm going to tell you about technology, but there's a big sociology piece to this. This takes the politics out of energy. So you can see here this is energy use, and look at where the US is. We're terrible. What I didn't show you is there's 13 countries worse than us. Right? Now, the reason I didn't do that is because the last president didn't like me and put me on an FBI watch list. And so when I promised him I was going to be a better boy, and when I would go overseas, it's cathartic for everybody to get angry at the US. And so when I showed this, they would get angry at me and be a little bit less angry at the past president. Now that he's not there, I guess I could put the other 13 countries on here that are worse than us, and there are. So you should know that. The United States is 14th ranked in energy use per person. And now I'm going to literally take the politics out of energy use, because you always hear that. There's too much politics in this. It's just science. So what did I plot here? I went to a DOE website, and I just took numbers, and I just made a plot. So you can do this at home. And what I did is I said, I want to see GDP per capita, GDP per person. So the United States is a very rich country, so we're way over here. We have a lot of money per person. And then I said, how much energy do you use per person? And I plotted it. So there's a whole bunch of good news and bad news on this plot. Here's good news. If you're the United States, look at, you're growing your GDP and you're not using more energy. So that's good. And now here I'm going to show you the danger of energy talks. I can bias you any way I want, because I could just tell you, look, we aren't using any more energy because we have great energy intensity, great conservation. That's partly true. On the downside, what I could do is grow a huge deficit and then let other people make stuff for us and then bring it into my country, which is what we're doing, and then let them get charged with the energy cost. All right? So there's two good pieces. There's a good piece of good news and bad news. We are doing better energy intensity, but because we grow a big deficit in trade, we're letting other people take our energy hit. That's why this is flatline. The other thing is, if you notice, I don't see any countries going the opposite direction. They're all trying to reach the US, and that's human nature because everybody's trying to get richer, so that's good. And so that's why the line's this way. If you want it, what you would want is the line going this way, actually the other direction, because you would be growing GDP and using less energy. And then the thing that's really troublesome is 3.2 billion of the current 6.2 billion people are on the lowest part of this graph. And they want to move up, and that's what's driving the energy use. Okay? I can do a different calculation. I told you I want 30 terawatts for the future. So what I could do is take 30 terawatts, divide by 9.4 billion people, and say how much energy use per person will I need. So if I say we all will live like an American, take this number and multiply it by 9.4 billion, you don't need 30 terawatts, you need 102 terawatts. And that's saying that the world will live like an American in 2050, which isn't going to happen. But you would need 102. If I say, to get to 30, who do you have to live like in the year 2050, but go visit that country and see their energy use today? Want to guess a country? Equatorial Guinea. Okay? Which isn't a high standard of living. So what I'm saying is you have to live at the primary energy use today of somebody in Equatorial Guinea, and I'm still going to need 30 terawatts. All right? So that tells you a different way how much conservation we're going to need, and we still need 30 terawatts. Remember, I still need 16 more terawatts. So right now we're using 14. We're going to need 16 with unprecedented conservation. Why? I kind of already told you. One reason is that it's from the 6 billion new energy users. There's 3 billion people that are going to be born in the next 40 years, and there's 3 billion low energy users, and they're coming up. So that's what's driving it. And I call that the non-legacy world because they don't have a big energy system right now. So that's what I mean by legacy. If you have it, you got to use it. So you guys have a grid. You're going to use it. These 6 billion people, they don't have any energy. So it's kind of like new fallen snow with no footprints in it. And can we get in there and do something good before it gets messed up? Right? The next thing is, if you're worried about carbon neutral energy or the environment or energy use, then my argument is you want to take care of these 6 billion people because they're the ones driving the energy use. I'm going to make the assumption that you in the legacy world will do the right thing and conserve. And if you don't want to, you will, because it's going to get so costly you will want to by the end of the day. And if it's the non-legacy world, people without stuff, they also don't have a lot of money, then the most important thing is low-cost energy, which is not how we live. I'll show you now in a few minutes why. But all I'm going to care about is cost. And the one thing you don't do is what we do in America, and that is whenever somebody asks how much an energy system is going to cost, you say, well, this is the current energy system. And then if you're going to use it for fewer people, I'll divide. I'll make it tinier. And the reason that doesn't work is when you take things that are made for you, the legacy world, not only do you have the cost of the thing, you also have to make it very efficient. I'll show you why in a minute. And therefore, you have a lot of other equipment around the edges to run it. That's called balance of system. If I make the system tinier, I don't lose. I still have all the components around it to run it. So it turns out when you go to tiny things, or fewer, I want to go to a single person, I can't take a nuclear power plant and build it for one person. All right? So that cost doesn't scale, right? Or a power plant. So the argument then is this is why you need scientists and engineers. So poor Al Gore, he doesn't ever get it quite right at all. I have to say that. And once again, he's messing up because he's walking around the world saying, we already have the technology, we just have to use it. Because he doesn't get this argument. you can't take technologies off the shelf. The technologies off the shelf, by the way, we should be using some of them. He's partly right for the legacy world. But those technologies will never be adapted to poor people because they weren't designed for poor people without money. They were designed for you with money. So that's why you still need scientists and engineers to invent new stuff. Okay? Before we get into the non-legacy world, I just want to show you the difference, because this is all complicated stuff when you hear it on TV and radio, but it really isn't once you start driving to it. So I'm going to talk about global versus local. I'm only worried about global, meaning I don't care about countries per se. I worry about a global population. Now, you have to choose a side. You can't do both, and here's a perfect example. On the left, you just have to look at the colors. This is energy in, and then this is how we use it over here. And then I've broken it out. So the green is all oils, gasoline. Black is coal, this is natural gas, and then biomass, hydronuclear. So if you look at this, it's around a 1/3, 1/3, 1/3 split between oil, gas, and coal. That's how it works in most developed world. The other thing is all the oil, you can see when you come over here, it all goes to transportation. In the Northeast, you use a little for heating, but it's the only place in the country that does that. So almost all the oil goes to transportation, coal and natural gas goes for electricity generation. So, and heating. So here, let me give you a local problem. The United States, we have large oil imports. It would be great. We will do biomass. We will do everything we can, and we will have no oil dependency. That sounds great, and it is for the United States. For the world, it's a drop in the bucket, and it hardly goes anywhere to solving the energy problem. And the reason is, if I'll tell you right now, we use 3.3 terawatts. If it's a third, if I take all transportation oil to biomass, then 1/3 times 3 is 1. I've only saved 1 terawatt of energy. And I need 16 in 40 years. So the United States getting totally off oil with biomass does very little to help the world population with their energy problems. It helps the United States politically. That's a local problem. That's not a global problem. How about all the people who say you don't have enough stuff? Don't worry, you do. All right, so I'm going to show you right now. This is from Schlumberger. They're the people who drill for the oil companies. So by far you have 200 years of oil. If you want to the biggest pessimist in the world, take every number and divide by 2. All right, you have 100 years of oil. 400 years of natural gas, divide by 2, 200. A problem for the United States, you know who the Saudi Arabia is of natural gas? The Middle East has 52% of all oil. Guess who has 54% of all natural gas? Mr. Putin. And if you think everything, he's also always at Davos. Everything he's doing is try to move the world to a natural gas world because he becomes the next Saudi Arabia. And you've watched them play the games in Europe, just so you understand what's going on. We happen to have a lot of natural gas, too, so we're playing that game. But in the end, I believe it's a deadly one for the United States, but that's politics. Here's the one you should really worry about. You have 2,000 years of coal. And I'm a chemist. You give me coal, and I'll make anything you want. I can make gasoline. I can make the plastic in these bottles. It's going to be a little bit more expensive, but there is not one process we don't know how to do in taking coal, and you can live exactly the way you do today, and you just use coal. And we have a lot of coal to boot, the United States. So anybody who tells you, don't worry, or worry, we're going to run out of fossil fuels, they don't know what they're talking about, and you don't have to live a different day in your life. All right, it's just going to be a little bit more expensive. So what that's telling you is at the end of the day, The real driver is the CO2 problem. Because if you're not worried about carbon dioxide and climate change, first, I wish I could be like you because I wouldn't have so many anxiety attacks. So I really do want to be like you. And then secondly, we have no problems. And if you're worried about it, then you have a big problem because you're putting a lot of CO2. And the discussion I just had with you was what kids do. Okay, so I just want you to understand, I'm not going to talk about climate change. I don't really care if people believe it or not. But I do care about dialogue and the level of dialogue. To say whether you believe in it or don't is what kids do. That's yes or no. The real question, because you now understand that energy use scales with GDP, gross domestic product, how much are you worried about it? How much are you willing to pay for it? And then as an adult, that's going to vary all over the map. And that's the discussion we should be having as a country. Not whether you believe in it or not. And the reason why you should always just discount anybody who says they believe in it 100% or doesn't believe in it 100% is because they're not a scientist and they don't know what they're talking about because nobody knows what the equation is that says T equals this amount of carbon dioxide. It's unknown in science. If you don't know the equation, you can't say yes or no. It's that simple. That's what scientists do. All right? So this whole issue of carbon is how worried are you and then how much you're going to pay for it, which becomes an adult discussion, right? And if you're going to pay a lot, remember, you're going to have to slow your GDP. And the economy's already in bad shape. So this is very complicated stuff. I wish I could make it easy, but... And then we have politicians who really screw it up. Okay, so let's do now global CO2. I just want to say a few things just so you understand the carbon argument, because I'm always on TV, and I hear all this junk from people. So let me just give you science facts. I'm just going to give you facts. And I'm going to just things that people love being misconceptions. They like seeding doubt in your mind either for or against. So the first thing is, this is the rise in carbon in the atmosphere since 1958. So it's going up. We're at 315 in 1958, and now we're at 380 in 2004. This is what's called the Keeling curve. If you watch the Al Gore movie, he made it sound like he invented it. Okay, so that's what that is. Okay. You should know that carbon has never been above 315 for 650,000 years. All right? That's a science fact. And the way that you can do that, that's easy. You go through an ice core, and then there are bubbles in the ice, and you just count backwards, like tree rings, and you go back 600. We've drilled deep enough to go back 650,000 years. There's a bubble. I put a syringe in the bubble. I take it out. I put it in the GC, and I measure exactly how much CO2 was in the atmosphere. So this is science. That's pretty easy to do. All right? So we've never been over this for... Have we ever been over 310 ppm? Yes, we have. It's been outrageously high at points in our global history. The problem is there wasn't 6.2 billion people trying to live off of the planet, and cockroaches were this big, okay? So when people say we've been there before, we were, but remember, it was a very different looking world that will not support 6 billion to 9 billion people. Right, so that's number one. Number two, I get this argument a lot when I'm on TV for the naysayers, is they'll always say, how could we do this? We've only been adding 2% of the carbon. So how can I go from 310 to 380 in a few years? We're talking about 650,000 years. And I can account, under that curve, I can show that every bit of it has come from us burning fossil fuels. How could that be? How could I go from 300 to 400 in 40 years with only putting a 2%? And what that means is there's this massive carbon flux coming into the atmosphere and then getting refixed by the Earth. And we're only perturbing it by 2%. So let me do a little calculation for you. You're a 200-pound person. You take in 3,000 calories, and then you try to expend 3,000 calories. I'm going to say over the course of 1 year, I want you to expend 2% less calories. You're going to add 2% on. So if you're 200 pounds, you're going to be at the end of a year 204 pounds. And then at the end of the next year, you're going to be at 208.2 pounds. And you can do the math. In 40 years, you're going to be over 400, 500 pounds. So that's what we're doing. There is a massive global flux. We're perturbing it every so slightly, but it's additive. You can't get rid of it. That's why this looks like it does. Some people say we can use the ocean because water plus CO2 makes rock. It makes carbonate. They're right. The ocean's big. The problem is when they do those calculations, I have to use the near ocean because the bottom of the ocean's really cold and there's a thermocline, and the water doesn't mix, hot water and the cold water. So unless I put a stir bar in the ocean and I can't use the ocean. It's a 1,000-year mixing time. Here's some great data. This has all been in the news. You've heard about it. Again, people were just saying it just was this East Anglia thing. And those scientists in England were stupid because scientists shouldn't do anything except explain data, and they were trying to spin. Here's some of the data they were trying to spin. Look at between 1940 to 1980. You see it going down? Here's temperature is going down. Temperature's red. And concentration of CO2 is going up from 1940 to 1980. Look at that. And that's real data. Okay, so if you don't want to believe in global warming or climate change, you say, aha, look at 40 years, it's going in the opposite direction. But I got to show you what that is to a scientist. Here's 450,000 years. That's noise. Okay? So here's how temperature and CO2 track each other for 450,000 years. But that's 450,000. I just took a 40-year snapshot here. People who make movies and use Hurricane Katrina, they're even worse. They're only taking 1 day. Are you getting a feeling I don't like Al Gore very much? And I don't like him because he's misrepresenting things for his story, and then it's very easy to attack. Right? So we should always keep this on a science data level. All right? So that's what is noise for a scientist. And what we do is we look at big trends over years, and that's what has us worried. All right? So just so you know, why scientists. So we're a bit worried about CO2. Let's look at some more complicated things. I'm going to make it really simple. We'll do some chemistry now. Carbon plus water, I make CO2 and hydrogen. Hydrogen you can use as a fuel. It's the most dense fuel. So I'm going to normalize the amount of energy in carbon to hydrogen. So if I take 1 carbon and mix it with 2 waters, I get 2 hydrogens and 1 CO2. If I take methane, CH4, and then I mix it with 2 waters, I get 1 CO2, but I get 4 hydrogens, meaning methane is twice as good a fuel as carbon. And that's why you're going to hear a lot about carbon credits, right? So you're going to have pricing of carbon. A lot of people want to go to natural gas because they're going to save a factor of 2 in cost if they're going to be charged for carbon dioxide. That's what this formula is telling you. Now let's get some really complicated stuff. If I take the amount, this is the stuff that people like at Copenhagen and Kyoto, and then everybody gets upset. And this is why. Because now I'm going to try to charge you for carbon. And you is every country in the world. And what you can see is the amount of energy used scales with the amount of carbon. So if you use more energy, you use more carbon. It turns out we're all on an oil line. So remember, coal's the worst. I put more carbon. Gas is twice as good. It doesn't get rid of carbon, remember. It's just half of it. And then oil's right in between. It's because oil, on average, has 2 hydrogens. So carbon has no hydrogens in it. CH4 has 4. Carbon has 2. That's why oil's in the middle. And you can see we're all on an oil line. The United States is a little bit below oil because we use a lot of natural gas. This is interesting. What country is continually out of step with the entire world? France. Okay, so here they are. Look at France. Now, that's why you're going to hear more and more about nuclear, whether you like it or not. Because France is heavily nuclear. And look if you're worried about carbon, remember, primary energy use scales with GDP. So they're growing their gross domestic product. They're becoming richer. They're using more energy, but they're not adding any more carbon in the atmosphere. So that's why you're starting to hear even environmentalists say, maybe we should consider nuclear, because France is doing the experiment for us. We can collect the data. OK, I'll get to more nuclear in a minute. So what this is telling you, and what the French have shown, is you have to cut the tie between carbon use and energy. It's the only solution. Okay? Now, we've had this problem before, so how are we going to do it? So I got this article. This is from the New York Times. Actually, Eric Morris is in the transportation department at UC Davis, and this is a great article he found. In 1898, everybody from around the world, another global problem, got into New York City because they were worried about desperation by horse manure. The situation seemed dire. The Times of London said that in 1950, every street in London would be buried 9 feet deep in horse manure. And this is true because people just extrapolated. And then one New York worrier concluded that horse droppings would rise to Manhattan's 3rd-story windows. And no possible solution could be devised, because they could never see that the automobile was on the horizon, which stopped that. So what this just tells you is shift happens. You like that one? I really worked up to that. So we can have shifts when you have technologies. You can shift. That's a paradigm shift, okay? And so obviously, and that's what we're saying now, is we need a paradigm shift in energy use that cuts our tie with carbon. But I like this because it just shows you when it looks really dire. All right? All right, so let's have some paradigm shifts. I'm going to now calculate a future for you. And this is, I got a lot of heat for this many years ago. Now nobody's arguing because they've all done the calculation. So here's the coal, oil, gas base of 10.2 terawatts. I don't want to touch that. And now what I'm going to do is I'm going to take, and this got a lot of people upset, because I took every plant on the face of the earth. I took all the land on the planet, and I said I'm going to grow the fastest growing crops, biomass, and I'm going to harvest it, and I'm going to burn it to its total energy max, which gives me CO2 plus water. Carbohydrate plus O2 gives me CO2 plus water, and I'm going to calculate how much energy is left. Do I get out of that? So if I take every crop on the face of the planet, I'll save enough for you to get 2,000 calories per person a day. I take everything else, you only get 5 to 7 terawatts. Okay? And that's taking the full reaction. We can't do that today in science. We don't know how to burn cellulose, hemicellulose, and lignin, the woody stuff. We don't know how to do that efficiently. So we can only burn sugar or carbohydrate. So corn, it's only the little yellow things. We leave the stalk behind. All right? I made the assumption that I could burn it all, and I can only get 5 to 7 terawatts. Why? And the reason is the theoretical efficiency, and this is all I'm showing you here, is I can take the amount. We know everything, a lot about photosynthesis. If I take, there's 2 photons in, I can calculate how much energy went in, and then I can see how much energy was stored. It turns out the theoretical efficiency is 30%. But plants don't absorb the whole solar spectrum. So then when I normalize, it's only absorbing 1/3 the light from the sun. That gets you down to 10.5%. You can never do better in photosynthesis. Right? That's the ceiling. It's the theoretical upper limit. And in my calculation, I took the fastest growing crops, which are 1%. Because remember, plants don't grow at night, right? And there's crop cycles. So you can't do better than 10.5. fastest growing plants are 1. Why do you hear about algae a lot? Algae are pretty darn good. They can get up to 5%. That's why you hear a lot about algae, which is amazing. They're halfway to the theoretical efficiency. So that's why they're tiny. How about nuclear? Remember, I'm just trying desperately to get to 28 terawatts now. So I need 8 terawatts of nuclear. I already told you it's carbon neutral. So all my things here I like because they're carbon neutral. So if I want 8 terawatts, then let's do this calculation. A nuclear power plant puts out a gigawatt. 8 terawatts divided by a gigawatt's 8,000. And it's 2010, so in 40 years from now is my mark. So 8,000 divided by 40 is 200, and that's per year. And so I need to build 200 nuclear power plants a year, or 1 every 1.5 days for the next 40 years. Okay? And I forgot to tell you, you decommission the nuclear power plant at the end of 50 years. So the one you started building today, just when you're done, you got to start rebuilding again to decommission the one. So you're doing it forever to give me 8 terawatts. How about wind? T. Boone and I went at this at the Clinton Global Initiative. I finally won. The easy way is he de-invested all his money in wind quietly over the summer when he found out he couldn't get you guys to invest in it so he could become rich. Here's the problem with wind. I can do the calculation, or I can just say this to you. Anything you can put your hand through this easily is not a good energy source. If you want to do the calculation, you can't create or destroy energy. So sun comes in. That's the driver for wind, solar energy. It's 100,000 terawatts. Take the atmosphere, divide it into thirds, lower, middle, upper atmosphere. 1/3 times 100,000 is 30,000. For the last 100 years, mechanical engineers have shown that the amount of energy transfer of sunlight to wind is 1%. 30,000 times 0.01 is 300. The land mass on the face of the Earth is 2/5. 300 times 2/5. All of a sudden, you're at no energy. That's over the entire face of the planet. T. Boone tried convincing people because he wanted you to invest in it, and finally the bottom fell out because that's just the physics of wind. But this is really all you need to know. And then dam every river. We've dammed every river. There's only a terawatt left in hydroelectric. So all the plants on the face of the Earth, I'll leave enough for you to eat. A new nuclear power plant every 1.5 days. Windmills everywhere. You're getting 2. That's 10 meters. If you go a little higher, you can get 100 meters. You can get around 4.5 to 6 terawatts. But that's over the entire face of the planet on land. And I dammed every river. So that's what you're in store for the next 40 years. That should scare the hell out of you. Because what you're going to do is just keep filling it up with brown, gray, and black. Okay? And that's why a lot of us want solar. So you can look at the numbers. There's a lot of it. The cloudiest day, there's a lot of it. All right? The cloudiest days in the world are in Bavaria. They have the highest solar market penetration. The cloudiest place on the face of the Earth versus the sunniest in Australia just means that you need twice the area of solar panels on your house. If you go to Australia, all my friends, academics, they always use solar. They're using 1/8 of their roof. So we're talking about half a roof. I'll show you at the end of this for a cloudy area. Sometimes people, you're going to hear in the future a lot about water too. Water, 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 water. And you should be worried about it because this climate issue is driving water issues. You should realize if you do the energy thing right, you go a long way to solving the water problem. So you drink in the US 4.84 trillion gallons of water. You use 70 trillion to just cool your power plants. Okay? So most of your water use, whether you've ever realized it or not, is to generate energy. For every kilowatt hour of energy you use, you're flushing half a gallon of water down the drain. The average American uses 30 kilowatt hours, so you're flushing 15 gallons of water down the drain, irreplaceable, to give you that power at your house. So if you get the energy thing right, you do a lot for helping the water problem. So why aren't people using solar? What everybody will tell you is photovoltaics are too expensive. There's two problems there. One is, 5 years ago, they were $8 peak watt. Now they're $1.25 to $2, depending. First Solar will be delivering $1, 25% peak watt. That's a factor of 8, and you haven't changed. So that's number one. Why haven't you changed? There's two reasons. One is that when you do your calculation, you're going to find out that it's still much cheaper to use coal at 3 cents to 5 cents per kilowatt. So that's the problem. It's not solar's too expensive, it's coal's too cheap. And you don't put a price on coal. So particulates, whatever you're doing with CO2, when the ocean rises by another half a foot and you spend trillions and trillions of dollars to protect your city, none of that's in the calculation right now. Right, so that's the first problem with coal. And then the second problem with solar is that if you can't store it, you're not going to use it because you can't use it when the sun's only out. Oh, where's my, wait a minute. Oh, don't look at that. Okay, so here's where the sun is out, and you can see here's the sun right here. And then here's what you use in energy, and you can see this is all missing. So you need to be able to store the solar so when the sun goes down, you can still use it. Right? All right, so that's sort of an overview. Now I have to go to what I'm worried about. Remember, I am worried about the 6 billion new people. So I have a second challenge, and that's cost. So I want to just show you this. I need to make things cheaply. And I told you at the beginning of this lecture, it's exactly what we don't do with energy. Now I'm going to prove it. Again, you can do this at home, because I just go on the web and do these calculations. So you just get the data. I took Boeing 777 and I said, how much does it cost to make? And then I said, how heavy is it? Just what's the weight of a Boeing 77? And I said, that's the number you get. And then I said, how many do you make a year? And then the year 2006, I think I took this, you made 75 of them. And then I put a plot point. And then I did it for etching tools, machine tools, and then finally automobiles. What this is saying is the cost is coming down for two reasons. One is this is lighter than that. So in a heavy manufactured environment, I'm telling you, I don't care what the stuff is that you're manufacturing, it's going to cost $10 per pound at the limit. And I'm telling you, the way to get the cost down is you make a lot of them. You don't make a few of them. So if you make a lot of things that are light, you're going to get the lowest cost, and you're going to asymptotically hit $10 per pound. This will not work for pharma, because that's a high-valued thing. It won't work for commodity chemicals. It won't work for Intel chips. This is stuff you make, just heavy-duty manufacturing, which is what energy systems are about. What do we do in energy? And here's the problem. This is why you can't do what we do for poor people. You only make one of them. You make one nuclear power plant. You make one coal-fired power plant. It weighs a lot, and you made one. It's off scale in the wrong direction. Now, how can I get away with that? It's because you're rich, so when I make it, I can take 40 years to get all my money back from you. Right? But if you're poor, I can't do that. So that's the discontinuity with the way we live for these 6 billion. If you don't believe how good this is, some of you already saw, look what, this means I have a relationship. I have things that are very different on the same curve. There's McDonald's, okay? So I got McDonald's hamburgers on there. So what I'm saying is, and that's about the truth, go figure out what it costs, and then put the tomato and the lettuce and the price per pound per meat, and you'll get $10 per pound for a hamburger from McDonald's. So what that's saying is if you're going to try to get energy to these 6 billion people, you can't do this, and you have to become the McDonald's of energy, which is light and fast throughput manufacturing. Okay? How does photosynthesis work? It stores energy. So I'm going to go through this quickly. You remember this probably, that light comes in, hits water, and it makes hydrogen and oxygen, right? That you probably didn't know. It makes actually NADPH, but light splits water and makes oxygen plus hydrogen. It then takes the hydrogen and fixes it with CO2. So what you remember is light, water, and CO2 makes oxygen and sugar. But the CO2 part doesn't store energy. Matter of fact, there's no energy storage here. Hydrogen plus CO2 to make sugar or carbohydrates, that's an engineering problem. Plants need to stand up, so they need to make cellulose. There's no energy storage here. All the stored energy of the sunlight is simply in water splitting. This is an engineering problem. This is called the Calvin cycle. So if I'm worried about energy, I don't need to do this part over here. I just need to split water. Now, what's photosynthesis really doing? So what's a fuel? Here's carbon, 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 hydrogen. That's gasoline plus oxygen. I'm going to burn it. Here we go. Okay, I just burned it. And I made water and CO2. So watch this again. The reason why you should watch this is anybody does PowerPoint. That took me 14 hours to do. Try to do that at home. It's that part that you never use in custom animation. That's what I used there. Okay, so I took a carbon-carbon-carbon hydrogen bond. I made CO2. So I took high energy bonds. I just rearranged them, and I took the excess energy and used it. What photosynthesis does is it takes low energy bonds of water, it rearranges them and makes high energy bonds of oxygen and hydrogen, and the sunlight drives that. So when the sunlight goes into the plant, it's simply driving the rearrangement of water to bonds, OH bonds in water to oxygen and hydrogen. You then use it in your body. And in case you don't believe that, I'm going to tell you something that's mind-blowing, because you probably have never thought about this, and you shouldn't. I don't know why you would until somebody tells you, so I'm going to. Photosynthesis is taking water to oxygen plus this hydrogen, this NADPH. And then the hydrogen gets fixed with CO2 and makes carbohydrate. You then eat the carbohydrate. The plant, what you do in your body right away is get the CO2 with the hydrogen. You get rid of the CO2, you breathe that out, and you get the 4 protons and electrons back. Then what you do is inside your body you have a thing called cytochrome C oxidase. It's an enzyme in your mitochondria. It takes the oxygen plus the hydrogen and electrons. So the O2 that the plant made over here, you breathe in. It takes the hydrogen from the carbohydrate, and then you make water, and you take the excess energy. And that powers you. That's what's happening right now in your mitochondria. In case you've never realized it, and this is the honest truth, I've taken light, I've rearranged the bonds of water to oxygen and hydrogen, and then CO2 to sugar. What are you chewing? So I put the light energy in rearranged bonds, and then you bite it. So when you eat a green leafy vegetable, what are you chewing? You're chewing the sun, if you've never thought of it. And that thing is then getting that energy, mitochondria, your cytochrome C oxidase, is coming out inside you in a way that you can use it. But you literally are chewing a piece of the sun because those photons have been stored in the rearranged bonds of oxygen, if you've never thought of it. So that's why I'm telling you I'm a throwback, because I just want to go back to this model. And what I would like to do is take water now, have sunlight hit it, and make hydrogen and oxygen, and then you can burn it in your house and power your life, just like you've been doing with, that's how we've designed this whole planet. So I can tell you, in 1 liter of water, if you take water and rearrange it, you can store 13 megajoules of energy. That's the MIT swimming pool. It has 3.2 million liters of water. If I can take, now I got to make this a power. Remember we were doing terawatts? This is energy, how much energy is in a liter. So now I'm going to tell you this thought experiment. Take this pool of water and convert it to hydrogen and oxygen per second to get a power. So what I'm going to ask you is take the volume of the MIT pool and convert it to hydrogen and oxygen globally per second to hydrogen and oxygen. You don't have to do it just here in Pensacola. It's going to be global. And remember, you don't use it up because when hydrogen and oxygen recombine, just like in your body, you get water back in energy. So you're never using it up. So I want to just basically operate on the MIT pool globally per second to hydrogen and oxygen. Guess how much energy you get? 43 terawatts. So remember I needed to get to 16 with all those draconian measures? What I'm telling you is you only need 1/3 an Olympic-sized swimming pool getting converted to hydrogen and oxygen globally, and I will give you 16 terawatts of carbon-neutral energy. And I want to do that for poor people. So that's your way out of this mess. Okay? But because it's for poor people, it has to operate out of just a glass of water. It has to be simple. If you operate under simple conditions, then it's cheap and easy to manufacture. I need to move towards McDonald's. And the hard part with splitting water with sunlight, by the way, and this is true in photosynthesis, is getting the oxygen out to leave the 4 protons and electrons behind. And that's called photosynthesis. That's what photosynthesis is doing. So up until 2 years ago, nobody could do the basics of photosynthesis, split water to oxygen and hydrogen, store light in the rearranged bonds of oxygen and water, just out of a glass of water. Now, you can go on the web and buy a commercial electrolyzer for $50,000 and do that. But they have to operate under super harsh conditions, and then you get those big balance of systems costs I was telling you about. This has no balance of systems if I can do this. So I'm going to go quickly now to end this. That fellow, Jim Barber, is a professor at Imperial College. He's a biologist. He, in the last few years, has figured out exactly what the plant looks like inside. And once, this is called the crystal structure, the Kodak moment of a plant. And once he got that, we could go in and look inside his structure. It's just a photograph, effectively, of the plant. And I could see what was splitting water. And the thing that was splitting water was a simple piece of rock. It's a dice cube of just manganese, oxygen, and calcium. That's it. Manganese, oxygen, and calcium. That's what's in rocks. And it's just a dice cube. It's being held in this complex network. Granted, the complex network is so that the plant can operate under benign conditions, right? The other thing we noticed is this plant, when you split water to oxygen, it's so vicious, it starts eating the plant up, and the plant dies. So every 30 minutes, the plant takes this big protein, it removes it, this cluster falls apart, so then the plant can't damage itself, and then it rebuilds itself, it refreshes itself. It fixes itself. That's different from the way scientists work. Scientists try to make things that are really stable forever. What we decided to do after we saw all this work from the photosynthetic community is let it be unstable, but just try to fix it. And so this guy, Matt Cannon, he's a professor now at Stanford in my group. When he was in my group, this is all you do. You take a glass of water, you take cobalt, which is an earth-abundant metal, and you take phosphate. You got to do it properly. And then you put a conductor in there and put some electricity on it. And when you do that, there's a movie running down there's lots of bubbles you see. What you do is you see on the surface, you get a thin film. It's only like really thin film, 100 nanometers for people who know that dimension. So it's like less than a hair thickness film, and then that film is capable of taking water to oxygen, and those bubbles, which are coming off pretty quickly, they're coming off with a unit of 10. I'll tell you what that means in a minute. Just remember the number 10 with that many bubbles. I'll just tell you quickly, all these guys, this has been a 2-year odyssey, we figured out how it works. The first thing is it's a cube. It's a molecule. Just the cube looks just like the cube of photosynthesis, but with cobalt instead of manganese. It forms spontaneously, because when you're in the glass of water, it's a pure water solution. When you put the electricity on it, then the cube forms, and then it starts splitting water to O2, and lo and behold, what all these guys have shown, it decomposes the cubes fall apart while it's operating. But the phosphate, remember I had phosphate in there? It actually drives it, it reassembles it. And so it's called self-healing. It's always fixing itself. All right, now let me tell you the importance of that. This thing is dirt cheap, works under ambient conditions, inexpensive, highly manufacturable, self-healing. Because we're in water, I'm splitting water only to O2. How am I making hydrogen? Everybody uses platinum. Fuel cells, everybody. Because we're in water, we could get rid of the platinum. So this is all getting patented by MIT. I'll just tell you, it's 2 and 3 earth-abundant metals we now have working better than platinum. So there's no platinum now, cheap metals, cheap cobalt, cheap substrate, and it's even better than platinum. The structure looks like the cube of photosynthesis. This is the structure of our cobalt. And remember, that's a dice cube, and photosynthesis is a dice cube. When I first had this discovery, people said, then why didn't nature use it? And I thought, yeah, why didn't nature use it? Just give me one more year, you can invite me back. But I think I figured how the Earth is breathing. And it's by an algae called Prochlorococcus deep in the ocean, and it's not using anything Melvin Calvin said, which was the Calvin photosynthesis of manganese. It's using the cobalt oxide cube of the one we have. So give me another year on that. And here's the cool thing. Because it's always fixing itself, you can use it in salt water. You can use it in river waters. So here's the Charles River. Here's pure water, 18 mega ohm water. It's super pure. That's what every catalyst that's ever been made before this one had to use. This blue line is the Charles River. Why can I use any water source? I can use human wastewater front and back. I'll tell you why that's important to me in a minute. So why is that the case? It's because nothing can grab onto it, because as things start to foul it, it's breaking down and it's healing itself. It's always giving a fresh face, okay? Why is it so important to me that it works out of human wastewater? First, the fact that it works out of any water means what happens if you give poor people water, but it's super pure to use an electrolyzer? They're going to drink it. So now they can go and literally just get a muddy puddle and start using it, or they can pee in a bottle. Now, why is that important to me? Because if I can take, a catalyst can take dirty water or wastewater to hydrogen and oxygen, when it recombines, I get pure drinking water too. And most diseases in the developing and non-legacy worlds from bad water supplies. That's my demo. I'm going to have to get that again. So not only do we have, because of this, it's operating simply, we can give distributed energy to people, and we can give them clean drinking water from any source that has water in it. Why is this important? Why am I so hot on this discovery? Here's the commercial electrolyzer you can buy. They operate at 1,000. The movie I just showed you was 10. So it's 100 times slower than this. But that comes with big balance of systems costs. And for 1 kilowatt, it costs $12,000 of energy. The DOE target for a kilowatt of hydrogen is 2,000, far off in the future. This is what's in my lab right now. It's just PVC piping. We have our cheap alloy, a simple hydrocarbon separator, my catalyst. We're building it for $28. We're faster than 10. We're up to 100 now, so I'm only a factor of 10 slower than this, but I'm $28 and this is $12,000. Okay, so now we can start talking about poor people. The other cool thing is, even the $12,000 thing needs clean water. I can use any water source. Okay? So that's where we're at right now. That starts to say, can you have sunlight? This is how you would live in even the legacy world. This is now off-grid. Sunlight hits the PV. Use the sunlight during the day to run your house, take a little of the electricity, feed it to my $28 thing, make hydrogen and oxygen, put it in a tank, then feed it to a fuel cell. When hydrogen and oxygen go in a fuel cell, you get current out. So I can power my house at night. I can recharge the battery to my electric car, or I could take the hydrogen directly and put it in a tank and run a fuel cell car. All right? So that's the model. And what you're doing then is only taking light into water, rearranging the bonds, and then you're releasing them for your use as electricity or in a car. For a house, for the average American house, it's 31 kilowatt hours a day. Remember, I'm running at 100, not 1,000, but I forgot to tell you, the output of a photovoltaic is only 20 milliamps per centimeter squared. I don't need to be at 1,000, I just have to be over 20. I'm at 100. So in less than 3.5 hours with 3.5 hours for a PV, photovoltaic, 6 by 5 meters on your roof, I can split enough water to store enough energy for you to use for 2 days, because during most of the day you'll be using the PV directly. I'll just take half of it to split water. So now people worry about storing hydrogen. You should worry about storing hydrogen in terms of volume, except most of the hydrogen discussions are for cars. You can't put that tank in your car. But you can bury this outside, and at 200 bar for a tank that big, 110 liters, I store enough hydrogen for 31 kilowatt hours a day, what you need. Right? This isn't Disneyland. It's happening. So on January 14th, Honda, who has all these beautiful fuel cell cars, but guess what they can't do? You can't take hydrogen and ship it around like gasoline, and you can't have hydrogen gas stations. It's not going to work. But you could think about building a house and do exactly what I said and split the water and just become your own gas station. So Honda is making a refueling station for the home. Because if they can do that, that cracks their problem with hydrogen distribution. They can start selling fuel cell cars. So this is happening. They're making a huge investment for the legacy world. I'm going to come in. They like me now because I'm going to come in with a really cheap way to split water for them, right? So here's how it's going to work. The PV is cheap enough. I'm telling you right now. Water splitting, cheap enough. H2O2 storage, cheap enough. Fuel cells, cheap enough. I can go on the web with using commercial stuff. Forget about what I just did. And for around $85,000, I'll build you this whole system using commercial stuff. So why aren't you doing it? Because when you go and do the price thing with coal, you're still going to come cheaper. That's number one. The other reason you're not going to do it, as soon as it breaks, there's no service industry for you. So there's got to be a tipping point here. But I want to just, this is a really important point. We can do this now. There's no science showstopper. The showstopper simply cost, right? And we just took a big step in reducing the cost. For poor people, the storage and splitting is now cheap. The PV will be cheap. We're entering a big agreement with a big company that's about to deliver us really cheap PV for the poor. The question is, can I get a cheap fuel cell? That's not obvious yet. So people like Honda and Toyota are back in Japan looking really hard to see what they can deliver me. We've done this before. Mainframes, this is how it was in the 70s. Personal computers. What's the mainframe of energy? It's this thing. Personal energy, follow the logic. This is all I can find now with, the only place you can find mainframes is in the dump. Look what's going to happen to the grid. I'm serious. I'm out to destroy it. That's what it's going to look like by the time I'm done. Just to tell you where it's going, because people always say, where is it going commercially? I'm a scientist. I can't organize a group. I can't take a group around a block for one trip. We get confused. So this is what you do. That guy, what I did, instead of staying with energy people who want to own everything, well, you just saw my logic. It's these guys. This guy invented the Ethernet, not internet, Ethernet, the LAN software, and he started a company called 3Com. He owns it. That guy invented the largest water desalination company in the world called Ionics. He went into retirement at 71 after selling his company to GE for $1.6 billion. At 75, 4 years later, I got him out of retirement, and I said, Art, do you want to try doing what you did for water desal with energy? So this thing's being run by these guys. It has lots of people, but it's all the computer people, not the energy people who want to own everything, because that's what the computer people had to do. The way this is going to work is with good partnerships. I have my thing, I need your thing, and your thing, and your thing, and we'll make this go. The energy people just want to say, I'm going to own everything, and then it takes forever or they shelve it. So this is happening. We have some good people here helping me. That guy ran the CIA, and that's not important. I'm ending with this. That's it. That's the amount of water you need for 31 kilowatt hours a day. I'm holding it. For poor people at 100 watts, remember now, this is for a kilowatt, 1,000 watts per hour. I could change people's lives with 1/10 that. The amount of water I need is 2 of these bottles a day to hydrogen and oxygen. And you don't use it up, it comes back, okay? So it's just about cost. We're very much on the verge. And if you think about it, it's the McDonald's, because it's all plastic, mold-injected, high-throughput manufacturing. So that's why it will happen. I'd like to thank you for your attention, and I'll answer any questions you have. Question. Wait, you got to get a microphone.
Thank you, Dr. Nocera.
Okay, now we got to put the microphone on.
Is it on?
Yeah, now it's on.
One of your earlier points was that the key to population control was educating poor women in the world. And that's one of my...
Poor people in general, but especially women.
But especially women, because that is absolutely accurate.
Right.
On the other hand, there is a paradox between the infant mortality rates in these countries and the number of children women have.
Yeah.
And that relates to the standard of living in these countries.
Right.
So if we could have a combination of your science and the political will and the lack of the chauvinism that exists in our country whereby we only want to take care of the people here and not recognize that we're all in this thing together.
Yep.
Anyway, I just wanted to get that point across.
Yeah. So that's really important what you said. Those things are connected. So if you get people a little bit more money, also if you get them clean drinking water, birth rates go down and they don't feel as compelled to have as many children. So there's one other thing you need to do, though, which I've come to learn. I'm 52. I've become so jaded. What you need is a bunch of smart people, I hate to say it, that can have a business model to make a little money off of the education of those people. So that's what's missing, is good business models where people actually, because they're not going to be altruistic. I've learned that already. It sounds like you are, I am, and we have no impact in the world. So we're going to have, so I look to people like GE who have 30% of their market in a capital fund, right? And I met Mr. Immelt a few months ago, and I said, why don't you try to figure out a business model to make some money off of educating poor people? So I really think, you know, it's again complex, but I think you also need that component or it will never have legs. But you're right about the heart part. It's exactly where you have to have your heart to make this work. Other questions? Oh, good.
You seem to be real good about forecasting and prognostication and so forth. And surely you must have some sort of research goals.
Yep.
When do you think this might come about?
Yep, perfect. So this is the plan. Right now, because of the science, we know it's working. So then the next question is, what really makes it a technology? And the technology is it easy to use and is it low maintenance, which I haven't proven yet. If it's not easy to use, or I put this up over there and then every year I need to send somebody into remote parts of the world to fix it, it's doomed. And so I'm giving myself 2 years to figure that out. The Department of Energy gave me a massive grant to help me do that. And then I will tell you, I'm hoping in under 3.5 or 4 years, we're actually making the system. I have some big people, big manufacturers, especially in the poor parts of the world. Mr. Tata, I don't know if you know Ratan Tata of India. He's ready to go, but I have to come in cheap. So the short of it is, I used to say 10 years. Then I went to 8.1254 years because I was on CNN and somebody called in and said, how come scientists always say 10 years? So if you go to 8.1254, they think you've thought it through. And now I'm going down to 4 years. And so if I don't do this in 4 years, invite me back and make lots of fun. You should, because I'm going to do it. And if I don't, then you should give it to me.
We have time for one more question.
In the back. You can yell. No, don't yell. We need a mic.
In trying to achieve ubiquity for your product, how do you combat business interests in the developed world who don't want it to succeed, and governments in the undeveloped world who don't wish to empower their population?
Right. So you're asking how you're going to distribute. So you need to go. So first you have to find people like Mr. Tata and get him on board because he can just jam it through because he's Tata. Okay. When you get to places like India, you need a lot of help. So I'm working heavily with UNEP, and I'm working with some of the big oil companies who have distribution rights through Africa because they know how to do distribution. But it's going to be very complicated. But how do I think it's really going to work? The way I really think it's going to work is what I'm seeing now. Oil companies make $40 billion a year. So the first thing is a bunch of really big companies that aren't oil companies are starting to realize if we can get $2 billion, that's really way over our 4% growth rate. So there's a lot of what I would call non-traditional companies. People like Air Liquide, French companies that handle hydrogen gas, fuel cell companies, who are starting to realize we start to get a profit because they become energy generators, not the oil companies. And so they have been very, very helpful in making this go because it's in their best interest. And then let me tell you, the oil companies have been absolutely great so far. I've had very little pushback, probably because they're not worried about me. They could snuff me out or something, I don't know. But the real reason is a lot of these companies are really repoising themselves as energy companies, and that really is true. And to give you a feeling, last year, you as taxpayers spent around $2 billion in basic science. Last year, the oil companies and renewable energy funding in the United States were up around $1 billion. So they're not what you'd think they are. They have the drug, which you keep taking. I always say, if you're really mad at the oil company, don't do this, do that, because they're not telling you to buy it. You are. But they are literally starting to poise themselves. They look at something like this and say, no, Sarah, if it flies, we'll own it, and we'll make it go. And this isn't so intimidating to them because they've never had access to this part of the world anyways. And they never will because they're never going to be able to build an infrastructure on it. So there's a lot of things going in my favor for this, actually. I don't really feel a lot of pushback, just lots of encouragement at this point.
Let's all thank Dr. Nacera again. Thank you.
Okay. But the bottom line is, I think we've turned the corner, at least as a society, and we're realizing we need to deal with this. So what I want to do first is tell you how you're living now, because a lot of people don't know that. And a few years ago, I did these global energy calculations. I'm going to explain. Every calculation I do, I can do in real time. So I'm going to show you how I do these in real time. So the first thing is I need to define a unit, and that's 12.8 terawatts. So that's not energy, that's power. It's a 100-watt light bulb. So when you have that light bulb that's shining on me right now, that's got to get energy to be powered. And so the power that you get out of that, you have to feed it. And this is a 100-watt light bulb. You're burning in 2000 a 12.8 trillion watt light bulb. That's what the amount of energy is we're using. And power is energy per unit time. So you don't need to worry about whether I'm speaking about today or am I talking about energy for a week. It's energy per unit time. And so we're burning a 12.8 trillion watt light bulb. And then over here in these numbers in parentheses, I'm showing you that almost all that energy that powers that light bulb comes from oil, gas, and coal. So I haven't told you anything new. In the year 2050, I can calculate how much energy you're going to need. And I'm going to calculate that it's 28 terawatts. So we're at 13 in 2000, and in 50 years from now, from 2000, so now only 40, we're going to need 28 terawatts. And that's an easy calculation, right? And it works. I can go into the future, and to test myself, I can go backwards and calculate in 1930 how much you used. And this formula works. And you just have to know three numbers. One is how many people are on the face of the planet, population. It's that simple. Okay. So let's talk about this issue about solar energy for the 21st century. And where's the mic? Here, I gotta be over here maybe? Oh, good. So this came from a journal called Science. It's a very prestigious journal. And Chimichan wrote, if our black and nervous civilization based on coal and oil should be followed by one with solar energy, that wouldn't be harmful to human happiness. And then what he said is it's to fix solar energy through reactions that master the photochemical processes that have been the guarded secret of plants. So here's a person that's in Science magazine saying we should probably use the sun and we should do it with photosynthesis. And that is very appropriate for the 21st century. The problem is, I kept the date out here. He wrote that in 1912, okay? And so if somebody writes something like that over 100 years ago and you thought that they wrote it last week, it must mean the most important thing is we're not really serious about this, right? Because nothing should be 100 years old and still ring true. So the first thing I'm going to sort of prove to you is we don't really care about energy, even though we say we do. I will say, and by the way, I'm going to start off, and it's going to sound very depressing. And by the time I'm done at the first part of this talk, you're going to figure, just go home and just wait until the world to end, okay? But actually, there's going to be a big message of hope. And the first message of hope is I've never seen more change in my lifetime in the last 10 years with regard to energy than anything else I know in society. I mean, it's on everybody's mind, no matter who you are, but all for different reasons. That's the only reason why it has legs. So it's a pleasure to be here. I'm going to have to explain that intro, it sounds like. I will, because there's a lot of science in there, but I'll be able to do that. I like to really thank West Florida for inviting me, and IHMC for hosting me, and then the Smart family. And it's always, there's two hard things in life. If you're the professor of energy, that means you have a chair. And if you're not very energetic, if you have a professor of energy, they take it away from you. And if you come and give a smart lecture, if you're not smart, I'm going to hear about it. So I'm going to try to live up to the family name tonight. And it's a joy to have Mrs. Smart here. So today what I want to do is talk about energy and in a different way. And you can see right here, it starts off, personalized energy for one person. This figure, I didn't even know this. I have a big research group, 40 graduate students and postdocs. And you really, I don't even know most of their names when it's 40. That's a joke. Somebody just went like this. They thought I did. But they all have talents, and they're always hidden talents. And this one fellow in my group who was the most inauspicious of anybody in my group, I found out is really famous in Japan because he created this character and he has this massive cult following. And if they meet Tim, they'll be very disappointed when they meet him. But this, I had him, because there are kids with purple hair that are all studded that visit my lab to meet the great Tim Cook. And I had Tim last year draw this because it gives you a sort of feeling about what I'm going to speak about today. And that is a single person. They're holding the sun in their hand, so it's going to be solar energy. It's actually an artificial photosynthesis, and I'll explain that dice cube to you later. And then that's the grid. That's how you live, and you can see I'm out to destroy it. All right, so that's what we're going to talk about today. I always made fun of the grid, and I know I can't destroy it, but engineers at MIT are really tough. And they've started yelling at me and saying I'm absolutely a lunatic for thinking I can destroy the grid, which all that says to me is they're actually starting to believe I'm getting close, or they would ignore me. So we'll see how close I'm going to get. So I want to get the energy right for one, and then this is the important point, times 6 billion, and I'm going to explain that. But it turns out everything in your society, that when you need a lot of it, you manufacture it, right? So if you need a lot of things, you make it, except for one thing, energy. In energy, you only make one big thing, and then you distribute it. So it's actually the anomaly in terms of how we live. And so all I'm doing, and what I want to do tonight, is talk to you about just returning to the old days of just good old US manufacturing. That's number one. And then go back really to the old days and then use the sun as your energy source, because you should realize we've only started using a different energy. So for 2 billion years, the Earth has been powered by the sun. And only in the last 200 years did we decide to take a different route, and we're screwing everything up. So I want to just go back for what we did well for 2 to 3 billion years. So if I know how many people there are. The next thing is GDP, gross domestic product per person. So in each country, I can take the United States and say, on average, we make this much money as a country and divide it by the number of people. So that's wealth, right? And then the last thing is energy intensity, and that means the amount of energy you use to drive a GDP. And so if I can use the same amount of energy and make my GDP go up, that's good. And that's called conservation. So all I did is I put a formula on conservation, which is energy use per GDP. Right? So if I know energy intensity, which is energy used per GDP per dollar, if I know how many people there are and I know how wealthy the population is, I can calculate energy for anybody. That's it. It's that simple. And so when you do that, you can get 28 terawatts. Now you have to figure out, what did I put in here for numbers? So the first thing is for population. Right now you're at 6.2 billion. You will be in 2050 9.4 billion. By the time I'm done speaking in the next hour, 240,000 new people will be born into the world, net. Okay? So this is going to give you a feeling of why we need so much energy. I used the GDP that was very conservative. I used the global average. And the reason why that's conservative is because it's 2.3% per capita growth. But it turns out that, for instance, China is growing at 6.6% this year. They've been up at around 10 and 12%. And even in this economic downturn, I was with the premier of China in Davos last year, and he promised they would grow at 6%.